Okay, so welcome everybody again to this next session of AI models and pipelines. And we will have this session with one industrial talk. So we'll start with the industrial talk, which is practical insights of repairing model problems on image classification, given by Akihito, and then we will have four actually, paper presentations following that. So you can ask questions through the chat or use your audio when after the presenters have presented. So welcome. Welcome, Akihito. Please introduce yourself and go ahead with your presentation.
Sure. So, thank you for introduction, Chair. My name is Akihito Yoshi. So, I'm working for FUJITSU Limited. I belong to a department working on AI-related research. Currently, my research stream is changed a bit, but still related to deep learning. So, let me present in an industry talk practical insights of repairing model problems on image classification. So I worked with two authors shown here. So before proceeding to the matter, let me explain about degradation. Even if a deep learning model is trained once, it can be retrained with additional dataset to improve accuracy. However, retraining sometimes causes a negative effect. For example, focusing on a specific sample in a test set, it can be changed from positive to negative. If another formerly negative sample is turned to positive in turn, accuracy is not changed on the surface, but a part of samples become deteriorated. In this talk, model repairing refers to fixing a problem such that correctly classified samples are changed to incorrect even if the model is updated. This notion is important in a real use case. Here are two aspects. First, input data comes from real world and contains noise or rare cases with small samples. In addition, secondly, accuracy is not a primary goal because, as I stated at the previous slide, a problem can exist behind the accuracy. So I focus on the second one, especially in this talk. So let me introduce techniques I use to fix the degradation problem in this talk. So non-retraining and retraining methods. As a non-retraining method, new recover aims at fixing a model problem by finding problematic weights in the step and then updating them in a neural network directory. So this method is a meta-heuristic based method and does not need retraining with many additional dataset. On the other hand, a retraining method can be a choice too. So we referred to a backward compatibility ML as a state-of-the-art method and apply for a model repairing task. In this technique, an additional term is added to typical loss function. So this penalizes when a sample which was correctly classified but become incorrectly classified after the retraining. So in this talk, I will mention multiple model repairing techniques stated before and then grasp insights, how they can be used for how they can be useful in consideration of a real situation based on experiments. Here is a research question. So what are advantages and limitations of each method considering a real use case? So we want to know what approach will be suitable for what condition. So we formulated hypothetical conditions and situations. So here we assume entire training and evaluation process as two steps. So firstly, a model is initially trained by a first dataset, and then the model is updated by a second dataset. So if you choose a retraining method, for example, the update by a second dataset corresponds to a retraining step. So we have divided our original dataset into 5 parts and then composed the train and the update changing ratio. Accordingly, the train denotes the first dataset used for initial training, and the update is for the second dataset. So based on these datasets, here are two arrangement settings. So exclusive and inclusive. As for exclusive condition, so you can imagine deploying a model, but initial training dataset is not available. The exclusive condition is further separated into two sub-conditions. So here, so if the train is smaller than the update, it can be assumed that continuous updates are needed due to variability of an environment. And the other subcondition is opposite. On the other hand, under the inclusive condition, the train is contained by the update. So this supposes that a model is trained incrementally by an additional dataset, including previous ones. So here is an entire flow. So we tried with fashion MNIST and Cypher10 datasets. For each, the train and the update in ratios mentioned in the previous slide, and the test dataset exists separately. So we use an 8-layer CNN training configuration shown here. So D train is used for the first training, followed by an evaluation. Next, the update is used for the second step. We use update method shown here. So the update phase corresponds to retraining as for the retraining method. On the other hand, a non-retraining method you recover adopts a heuristic approach for updating. So after the entire training process, so we can calculate metrics. So here, based on the size of each subset, which denotes classification results P1, N1, P2, and N2. So especially we will focus on BEC and BR. So BEC is taken from the backward compatibility research. So higher BEC indicates that both errors between M1 and M2 is kept. Therefore, the classification error of M2 is not new. And BR is taken from the new recovery research. Lower BR indicates degradation as the M2 classification phase is fewer. So higher BC, and lower BR is better. So we iterated entire training process 5 times, and each value, so here is averaged. So please let me focus detail on the next page. So here, accuracy is converted to relative value in order to observe difference of absolute data size of each data set. So you recover got a relatively higher score, BC and BTC, and a lower score of VR. However, accuracy improvement is smaller, especially in the condition where the update is smaller. In this case, a 4 to 1 condition, the decline of the accuracy is moderate. On the other hand, backward compatibility got a stable BEC even when the accuracy improvement is smaller, or BR is higher than CCE. So CCE deals a categorical, traditional categorical cross entropy. So from the result, each method had some characteristics. So add show here, and almost the same as the previous slide. And here are some lessons. So here, so practitioner can choose method depending on a purpose and a dataset arrangement. So for example, so consistency of the prediction is needed. So higher BEC can be a choice, and retraining performance with partial important data. Improving partially important data is important. So lower BR and higher BEC or BTC is can be a choice. So and if almost same, the metrics are almost same between them, techniques can be mixed. And as shown here, so accuracy does not always and has the priority from the aspects of the degradation of specific data samples. So wrapping up my talk, so here is some future work. So although we assume each condition is static in concern with a practical situation, the condition can change during the real-world operation. For example, even if the D train is larger than the update initially, the D update will grow during the operation time, resulting larger size than the train, D train. And the other aspect, noisy data including rare cases I mentioned at the beginning, is yet to be examined. So this concludes my presentation. So thank you. Back to chair.
Thank you very much, Akito. We don't have any questions in the chat. Maybe I can start the discussion. I was thinking, how does your approach scale with extreme data scenario? Because here, I assume with the backward compatibility, it's a lot easier to adjust the weights with the penalty, but you have to sample out and adjust the weights with the misclassified data points. How does your approach scale with large data sets, which characterizes most of the production systems?
Thank you. Yes, the aspect is, I think this aspect is also important, but currently we are testing with some limited open data set. So, such discussion is a future work for us. Thank you.
Yeah, thank you. If we don't have another question, maybe a quick one, and maybe you can also think for later discussion. How does concept drift, how is it incorporated in because sometimes misclassification of of a data point might be as a result of a concept drift. How does that how is that being captured?
So at the next step, we might able to introduce some. We might able to simulate some multiple types of noises, including concept drifts, such as changing labels, so or introducing noises in each image. So this is a possible experiment, additional experiments.
Okay, thank you very much. Maybe there'll be more questions at the end.
Thank you.
Next, I would like to welcome Eric for paper presentation, research paper presentation.
Yes. Hello. Can you hear me?
Yes, we can. Are you able to share your screen?
Let's try.
So Eric will be presenting a paper on UDAVA and unsupervised learning pipeline for sensor data validation in manufacturing. Please go ahead.
Yes. So just to confirm, you can see my slides?
Yes.
Yes. Okay. Perfect. Yeah, so hello, my name is Erik Susum from Sintef Digital in Norway, and I will present to you, as you said, our paper, UDAVA, an unsupervised learning pipeline for sensor data validation in manufacturing, written together with Simeon Tverdal, Arda Götnil, and Sagersen. So I will start by giving some context to our paper. We have been looking at AI engineering in the domain of manufacturing and specifically in processes that involve machining. So these are processes that are usually highly automated by using programmable machines and robotics, and the production of a certain part is repeated over and over. So such productions are normally monitored by a range of sensors, and we can see some examples in this figure. The challenge is to actually use all this sensor data to discover faults and drifts in the production and finding ways to do this automatically. We want to look at what we call sensor data validation, and by this we mean identifying behavioral modes in the data, verifying, for example, that a production cycle is normal or whether we have some anomalies and deviation from what we expect from a normal production pattern. So a challenge in this context is that in many cases, even though many companies collect a tremendous amount of data points because they have so many sensors, they have no labels of anything, either indicating deviations or errors, or simply labels of different parts of the production cycle. So this makes it challenging to use traditional supervised machine learning to validate this data. And because of this, we have explored using unsupervised learning or clustering to perform this sensor data validation, which means that we can utilize large data sets without relying on having labels. And we have looked at how we can engineer such a system so it can be used in industrial production platforms. So to explain our approach to this problem, UDAVA, that is the name of our tool we have made. It stands for Unsupervised Data Validation. And using this tool is a three-step process. So the first step is to actually have some sensor data to use for training. We call this reference data. It should contain sensor data from optimal or near optimal production cycles, because this will in effect serve as a baseline for comparison with subsequent production cycles. So this reference data goes through certain pre-processing steps before we create a cluster model from it. The pre-processing steps involve dividing the time series. In this case, we have some sensor values over time. We divide it into subsequences and compute what we call a feature vector that consists of certain summary statistics. So we have chosen to use 6 different features: the mean, median, standard deviation, variance, range, and frequency, common statistical properties that is computed from each of these subsequences across time. So this window size could be as large as several hundred time steps. So we get a significant dimensionality reduction down to only 6 features. And it's these feature vectors that we actually perform the clustering on. We also scale the features down to give them equal weight for the clustering. We can visualize the results of this by plotting the cluster labels back into time, the time domain. So in this case, we have colored the time series according to which cluster the corresponding feature vector belongs to. So we can see different parts of the time series get different cluster labels. The next part is to deploy this cluster model in what we call a sensor data validation service, where we have sensor data coming from production, where it goes through the same pre-processing steps. It is labeled by the cluster model, and we can see visualize it in the same way, but we also calculate something we call the deviation metric, which is this black line you see in the plot in the bottom right. So to explain this deviation metric, let's first take a look at some data points that have already been assigned into clusters. Each of these dots represent one feature vector. They are originally in 6 dimensions, but we plot them in 2 dimensions, just picking 2 of the features and plotting them to make it easy to visualize. That is why it seems like some of the clusters have some overlap. And these diamond markers represent each of the cluster centers for the 4 clusters. So one way of measuring a deviation from this could be to measure the distance from a new data point and to its own cluster center, the center of its own cluster. But being far away from the cluster center does not necessarily mean it's a deviation. It could simply be on the border of 2 clusters. It doesn't mean that it's an anomaly in the production. So instead, we propose using the sum of all these distances as a deviation metric. So if we consider a new data point f that's slightly outside in the periphery of the data points, it has a distance d to all of the cluster centers, and the deviation metric we have defined is the sum of all these distances. So that means if a new data point is far away from all the known clusters, it will have a high deviation metric, and it might indicate that we have a drift or a significant change in the production. So let me talk a bit about the deployment of our tool. We have created a simple and open API for receiving and sending the data and sending cluster labels and deviation metric as output. So when sending a JSON request, one needs to include the model, the unique IAD of the model one wants to use, because the backend can contain multiple models, and of course the time series data and the variable names. So the backend will then pre-process the data and label it according to the cluster model, and the JSON response will contain the SEM metadata and the cluster labels and deviation metric of the data points. We can take a look at an example of a JSON request. Here we have 6 data points of spindle torque, which is one variable from a production cycle. And in this example, we use a window size of only 3, just as an example, which means that we will have 2 subsequences. So the response will contain the cluster label and the deviation metric for each of those 2 subsequences. So to evaluate the tool we have made, we ask ourselves whether UDAVA can discover process behavior patterns and whether we can use UDAVA to detect changes like shifts or drifts in the production. We also have looked at how we can deploy it, test it, and maintain it, and what challenges do we meet when deploying it in industrial production environments. So in the paper, we had 2 different use cases. I will only present one of them now. It's from the aerospace domain, where we have a machining process that's broaching turbine disks for airplane engines. So the turbine disk is shown here in the red square, and it moves. It's probably easier in the schematic to see how it works. The turbine disk is moved up past 3 tools, that is broaching, removing some material to create these slots in the disk. And the disk is placed at a certain slot angle. We can see here 15 degrees in the example. Each of these 3 tools removes some material to create the slots. So we can take a look at how Udava labels data from this process. We had 2 accelerometers. This is vibration data from one of them, where the 3 different tools are shown over time. And the green and brown cluster appear when the machine is actually broaching, while the blue cluster appears when there is movement, but no actual broaching. So the clusters can then be used to detect or segment different behavioral modes automatically in subsequent cycles. We can actually compare the reference data at the bottom here. This is the data that was used to create the cluster model, and the data from a later slot. The reference is from very early in the production cycle, while slot 45 is very late. And a general trend we see is that the green cluster becomes more prominent, which means that the amplitudes are higher, basically higher amplitudes in vibration. And we can also take a look at the deviation metric for this. Just to explain, we expect some change in the production because the tool wears quite significantly over time. So we expect the data to look differently for each slot. If we look at the deviation metric for these 2, the yellow one shows reference deviation and the green one shows for slot 45. We can see that the deviation is high. It's higher on average and also have higher peaks in general. And if we then look at the deviation metric across slots in this plot, we see the tool wear in green, blue, and red for the 3 tools, and the deviation metric in black. So the tool wear increases for each slot, and so does the deviation metric, except for this point at slot 36, where we have a sharp drop. It actually coincides with the slot angle also being dropped at slot 36. So the deviation metric seems to be affected by tool wear, but it needs to be calibrated under certain conditions, for example, slot angle. So in conclusion, we see that the deviation metric helps to validate the sensor data, and it can also be used to reason about the cause for deviation by comparing it to other parameters. Finally, when talking about deployment and the actual AI engineering of this pipeline, we have used something called DVC, or data version control, for versioning the data and the models. So it's a big part of the backend of the pipeline. It also is used for tracking the different input and output for the pipeline stages, and it makes it easy to have the different assets in cache. We have also identified several challenges with regards to the AI engineering. We see the need for improving the greenness of pipelines, reducing pipeline depth. Also, in many cases, we see a potential for using federated learning for data security, and also the potential for using continual learning and domain adaptation to improve models over time. So I see I'm running a bit out of time. I'll try to be quick. Just one example of how this tool is actually deployed in an industrial environment from one of our research partners. So it can be incorporated into proprietary platforms, actually. So, lastly, moving on to future work, we have several ways ahead of vision. So one of them is to have AI-driven control of manufacturing processes, where, for example, the deviation metric can be used as an indicator for when processes need to be adjusted. We also see the potential of using Udava for data synchronization or of multivariate sensor data. It can be used to actually pinpoint the most likely synchronization points, even though we have very different sensor types. And lastly, having user involvement into the system where domain experts can help create better models by labeling the data. So that was all. Thank you for listening. And if you have any questions, just go ahead. Back to the chair.
Yeah, thank you very much, Eric. Wonderful talk. While the next presenter is preparing, there's one question here from Andre, who's asking that Udava API seems to work for batch-based. Have you considered streaming data in the cases of streaming data?
Yeah, so that's actually a very interesting question because with the partners we have in our research projects, we see different needs. Some work with databases, some work more with streaming data. So the early version that we have made now, it only works through this batch processing, but there's definitely a need to expand this to work with streaming data as well. And to make it more usable in systems that companies already have deployed. And whether one wants to do this in a general sort of online manner, or if one wants to do it offline. So, but it's not something we have implemented yet. Yeah.
Okay, thank you very much. We'll have more questions at the end of the session where we have all the presenters back for discussions. And now
Yes.
I would like to welcome Daniel, who will be presenting a paper titled Black Box Models for Non-Functional Properties of AI Software. Go ahead, Daniel.
Right. Eric, could you mute yourself?
Sorry.
Thanks.
Okay.
Okay. Yeah, so I'm a PhD student at Osnabrück University, and in this presentation, I'd like to talk about the challenges designers of AI products and product lines face, specifically when designing products that run on the edge, so on actual hardware and not just somewhere in the cloud. To illustrate this, I'd like to look at a small example. So let's say we are designing an AI product for usage in an agricultural setting. So we want to, for instance, be able to perform semantic segmentation for harvester control. So similar to self-driving cars, but with much more relaxed latency requirements as we have much slower devices. Or we may want to perform obstacle detection to aid drivers in a non-self-driving case so that they can still have emergency brake in case something goes wrong. And we also want to perform plain old classification, for instance, to identify harvested items and classify them into several categories. Now, when building such a product that runs on actual hardware, there are various different constraints and optimization goals for each use case, and possibly also between different customers. So, of course, there are latency and accuracy requirements for the inference process itself, but also aspects such as the hardware cost. And all of these are intertwined with each other and also affected by even more attributes, such as, for instance, the memory usage. So if we decide to use extremely cheap and simple hardware, we may not be able to use certain AI architectures because, well, they simply won't fit into the available system memory. So all of these different functional and non-functional properties are intertwined. And when developing the system, the question is, which configuration should we use to actually build a product that is not too expensive, sufficiently accurate, and so on. And we also want to answer seemingly trivial questions such as, well, if we have a GPU acceleration available, should we just ditch CPU-bound TensorFlow Lite and instead use GPU-accelerated TensorFlow because, well, that's surely going to be better, right? I'll get back to that question at the end of the presentation. So just to illustrate why this is such a difficult decision, here is some of the variability one is faced with when designing such a system. So for each of our 3 tasks shown in this example, we have dozens of available AI architectures, of publicly available AI architectures that we can build upon. Then we have various AI platforms we can use for inference, possibly also with post-training quantization. Then, of course, there is the hardware platform that actually runs the inference. And there are also runtime settings we need to consider, such as batching. Now, if we had a sufficient amount of time, we could simply build each individual system, benchmark it, and then, for instance, identify Pareto-optimal system configurations, pass these on to stakeholders, and let them decide, okay, these are the 3 systems that we are going to build, and the rest is not important for us. But in practice, especially with scalar configuration variables such as the batch size, that's, well, takes a bit too much time. So it would be much better if instead we were able to use black box models, which are fed with a configuration description of our system and then predict non-functional properties such as, for instance, latency or memory requirements or hardware cost. And of course, no one wants to manually build these models. So our goal is to automatically generate them from a suitable subset of configurations that we build, measure, and feed into a machine learning algorithm that generates a non-functional property model, which we can then use to predict non-functional properties of our product line. And that is precisely what we are looking at in our paper. So first, we want to answer whether this is possible in the first place, so whether we can automatically generate models that are sufficiently accurate when using them for prediction. And while at it, we also want to find out whether the generated models are usable not just for prediction, but also for looking at them and understanding the way the system works. So are the models interpretable, and are there any interesting observations we can gain from, well, actually looking at the generated non-functional property models, for instance, looking at the throughput model or looking at the memory usage model and so on. Next, so in contrast to the majority of related work in this area, we are not looking at the optimization of specific neural networks, which is, for instance, the case in neural architecture search, and are therefore not focusing on white box models that are capable of predicting the performance of arbitrary neural network architectures for specific hardware. Instead, we want to address the question of, well, which neural network architecture is interesting for neural architecture search or transfer learning in the first place, and on which hardware platform, AI platform, and so on should we run the inference in the end. Next, I'll give a quick overview about our methodology and then provide a few examples of accuracy results and observations we made based on the generated models. So in order for us to be able to make measurements, we first formalized the product line we are looking at. I've already shown this in the introduction. So we are looking at several dozen AI architectures, the TensorFlow and TensorFlow Lite AI platforms with optional post-training quantization for TensorFlow Lite. We are considering hardware platforms ranging from relatively cheap and small IMX8 boards and Raspberry Pis, all the way to powerful NVIDIA Jetson Nano and Jetson Xavier boards. And we are also examining the effect of the batch size. Now, before we can train a model on system configurations, we need to transform them into something that the model can understand, so a feature vector. For scalar variables, this is simply an integer variable. And for choices or alternatives, for instance, different quantization methods, we have 2 options. We can either use Boolean variables, so one variable for each quantization option with the constraint that at most one of them may be enabled at any time. Or we can use a single categorial variable that describes the quantization method or has the special null value indicating that quantization is not being used. For the actual modeling method that predicts how the system will behave, how its performance will be, we decided to focus on decision trees. as these can automatically generate the tree structure. So unlike, for instance, neural networks, there is no need to manually specify how the structure is working. And they are also easy to understand as they are simple trees, and also tend to locate more important configuration options at the top of the tree and less important options at the bottom of the tree. Specifically, we are looking at classification and regression trees, and a variant of them called data-efficient classification and regression trees that ignores scalar variables. Those have been shown to be quite good at prediction in the software product line engineering community. Then we are looking at linear model trees, which can predict piecewise linear functions, and extreme gradient boosting, which uses an ensemble of several classification and regression trees to better predict nuances in the behavior of the underlying system. For the tree structure, we are also looking at two different methods of building the tree related to the binary versus categorial decision mentioned earlier. So we are looking at binary tree structures using Boolean variables, which is pretty much the conventional method of building these trees. And where possible, we are also looking at categorial trees using non-binary nodes. So if we have, for instance, the quantization variable, then we have one node describing the quantization variable and one child tree for each of the different quantization methods we are looking at. The advantage of this is that in this case, the generated decision tree is much, much closer to the underlying feature model. So we hope that it can aid in understanding the model, and it also leads to more compact trees. Now, for accuracy and interpretability, here I just brought a single result. There are more in the paper. And that is the result when predicting memory usage during inference, which is quite important for hardware selection. If the model requires more memory than our hardware has, well, we don't need to try. So first of all, on the left, we see the generalization error after cross-validation, and on the right, the model size, so the number of nodes in the tree. And first of all, we see that there is no clear relation between model size and generalization error. So that's quite interesting. Bigger models aren't necessarily better. And in the end, in this case, the conclusion is that linear model trees perform best. They have both the lowest generalization error with 13 to 14% in this case, and also generate the smallest tree structures. This is also our finding not just in memory usage prediction, but also when predicting other non-functional properties, such as, for instance, throughput or model size. Now, for observations, although the generated trees are relatively large with 1,000 to 2,000 nodes, humans are still pretty good at identifying like patterns and structures in such models. And indeed, this is also the case for the models generated here. For instance, when looking at the model for throughput in frames per second during inference, we find that many configurations have a subtree where the throughput for the TensorFlow Lite platform is modeled as a constant, whereas throughput of TensorFlow is a linear function dependent on batch size. So it looks like batching does not affect throughput on TensorFlow Lite, so it seems to be useless there, whereas it's helpful on TensorFlow. And we also found that the constant part of the TensorFlow Lite throughput is actually higher than the constant part of the TensorFlow function in some cases. So it seems like TensorFlow Lite is faster for lower batch sizes and slower for larger batch sizes. And indeed, our data confirms this. Here we see the throughput of classification inference using MobileNet v3 on a Jetson Xavier board. TensorFlow Lite can only run on the CPU. TensorFlow is using GPU acceleration, and we see that for a batch size of up to 10, TensorFlow Lite is actually faster than TensorFlow, even though it doesn't have GPU acceleration, which can be explained by the overhead due to GPU acceleration, but still isn't something that we originally expected. So this is, to us, this was quite an interesting observation. So in conclusion, in our paper, we show that considering the interactions between hardware and software and modeling them is important, and black box models for these AI software systems can provide valuable insights in system performance and system behavior. overall, we find in our evaluation that linear model trees perform best, with an error of less than 13% in abstraction and less than 26% in generalization, depending on use case and non-functional property. And categorical tree structures are also useful as they are more compact, but have about the same accuracy as their Boolean or binary counterparts. And with that, I'll be happy to answer any questions you might have.
Thank you, Daniel. I do not see any question in the chat yet. Okay, there's one from Luis. So Luis is asking, from your observation, when should one opt for TensorFlow Lite? I find this result quite useful for green AI.
Well, the whole point of this research is that there is no general answer, unfortunately, because TensorFlow Lite often does come with slightly lower accuracy as it uses quantization. So if you can handle a small drop in accuracy or have models that are specifically built to also work well with TensorFlow Lite, then it's often useful if you are not interested in high throughput scenarios. So if images come in one after another and inferences run directly immediately on each image, then TensorFlow Lite is quite a good choice. But if you want to achieve high throughput with like batches of 30 or 40 images at once, then TensorFlow Lite is probably not a good choice, though. In the end, the answer really depends on your specific setting and requirements.
Thank you. We have time for more questions later on when we have the presenters back. But for now, I would like to invite the next speaker, Ahmed. Please go ahead and share your slides. So Ahmed will be presenting a research paper titled Improving Generalizability of Machine Learning-Enabled Software Through Domain Specification.
Yeah, I have a problem with the sharing. Just a second. Security. Yeah. Wow. What is that? I couldn't find it. It's a Mac.
You have to give access from your system preference. You have to give
system.
And you probably have to go off and then come back.
Okay, sure.
I will Chrome to display your video.
Yes.
Display on the screen.
Once he has done the system changes, he has to
go offline, fix it, and then again open Chrome again.
Okay. Okay.
Okay. While we wait, can we have the next speaker, Marcel? Just maybe testing your setup.
Yeah, I'm here. See if it works for me.
Yeah. Maybe you can also go ahead.
I can. Yeah, that works.
While we wait.
I don't mind.
Yeah. So go ahead and present your work.
Okay. Yeah. Great. Well, my name is Marcel Datring. I work. I'm a scientist at the Fraunhofer ISST in Dortmund. For everyone who doesn't know, Fraunhofer is it's one of the largest research organization in Germany. Our institute mainly does data management and data sovereignty related things, as in this study. What we've done, it's titled Data Sovereignty for AI Pipelines. And I'm going to present you the lessons learned from an industrial project we did in cooperation with Mondragon, which is a very large Spanish organization. I will briefly cover, or mainly cover 4 things. I will briefly start with the motivation and background, then present the case study. Show our results, which is mainly the lessons learned, benefits and barriers we saw in this project, and then have a little conclusion at the end. So the main motivation of our research was that we saw that in collaborative AI pipelines, you need to have the ability to share data with your partners. So you might want to share data for a variety of reasons because you don't have the tools or you don't have the AI know-how or whatever. So there might be some rationality to work together in this context. And what we also saw is that this sharing of data is always really complicated. So it results in the establishment of data governance anti-patterns, as we saw in some literature. To give you a concrete example, in this case that we had at Mondragon, when they wanted to share data with an external partner, this was a process that usually took weeks to months to do this. And this, of course, is far from any real-time analysis. And it required a lot of manual work to achieve this. And it was really complicated in the end. So, of course, we mainly have this problem between different companies that is especially challenging, but also within a company. Like Mondragon is a really large company. It has over 80,000 employees. And of course, there were different business units that are reluctantly to share their data with other business units, even if it's within the same organization. So we looked for a solution, and we found that actually there is not much of a solution at all, and definitely none with regards to AI pipelines and the whole machine learning domain. So we decided to conduct an action research study in cooperation with Mondragon and delve a bit deeper into this topic. Our main research question was quite practical, titled "What practices are applied to realize data-driven AI pipelines?" So basically, what do we need to do to get there? And what are the benefits and what are the barriers of these? To briefly go a bit into more detail into the case study, Mondragon wanted to share data with an external AI service provider. So in this case, it was a data quality service provider, and they received some sensor data sets and analyzed these for a potential concept drift. So they did some more or less basic data quality analysis and then sent the result or the model they trained back or made it available in the end. And that was actually the main requirement. So the main requirement was that both Mondragon and the service provider, they wanted to operate on the same terms to achieve the level of trust they needed to realize the data sharing, the automated data sharing. And we also defined this a bit more concrete. So they both wanted to be data to be used under agreed terms. So they, for example, wanted to specify that this data should be available for like a month, a week, or a day, and after that, no longer. And then that the other partner can only use it for that time. That access can be revoked at any time. That they share the same execution environment to avoid or just to ensure that there is no accidental data loss or whatever. And that data is deleted from the other side upon request from the other partner. We did a little bit of research on what technology might be best suited here. We decided to go for the IDS data space connector, which is a connector that allows participation within IDS data ecosystem. IDS stands for International Data Spaces. So they provide information models and standards for establishment of data ecosystems, more or less. On the right-hand side, you can see a little bit of a sketch on how the architecture looked like. Mainly, it's the factory, which is Mondragon in this case. They have a data space connector and the service provider as well. And between these connectors, they are enabled to share their data in a sovereign way. Sovereign means in this way that they retain access and control over their data despite sharing it. So for realizing our use case, we needed several components, actually three. We needed a backend component at Mondragon. That was mainly an application that collected data from the machines, so the sensor streams. They did a little bit of data preparation and then forwarded it to the connector. They've done this with mainly RabbitMQ and Node-RED. Then both participants, as I already noted a second ago, needed a data space connector. which enables the participation in the IDS ecosystem. And of course, on the research facility or AI service provider side, we needed a data app, which is the application that offers the trained model to within the ecosystem. So it kind of is a wrapper to the model to make it accessible in this ecosystem, because that was needed because there is they need to have the same execution environment. It needs to follow the same naming and information models and stuff like this. So coming to our results. First of all, how did we get here? We conducted our 12 months project, and over the whole project, we gathered a lot of data in the form of technical documents, of meeting notes, of emails, or any other kind of exchange we had with each other. And then we conducted a full day workshop and to reflect on the design decision success factors and stuff like this to generalize our experiences and findings and the findings we made. To categorize our results, we used the data challenges model published by Gröger, who also had a look at what data management challenges there are in AI pipelines. In his view, there are 3 of them: data management, governance, and democratization. And we try to relate our lessons learned to these challenges to kind of provide a way on how to address these challenges, at least for similar use cases. I'm not going to cover all of these lessons learned because that would be quite a lot. I just want to point out the most important one, or maybe most important one in this case. The first one is that we needed an independent trustee. It's a number 2 here. That was probably the most important thing, because there was no trust between 2 partners. And so what they needed is that they needed kind of a third party to be involved in the whole data sharing that guarantees that the same technologies are used, and they guaranteed that they follow the same information models and things like this. And that kind of helped, even so it's not going to work all the way down your business processes, so it stops at the connector level mainly, but just having this guarantee helped to build up kind of a level of trust. What's also quite important was a need for real-time support, and we heard this in a previous presentation. Having real-time was, I think it was quite important, because we also followed kind of a batch approach before, so just having forwarding batches of data. We found that this was not enough. It definitely ends at having real-time analytics at some point. And so coming there, I think is an important step to go. And then, of course, maybe another very important thing is that we needed a solution for standardization, which kind of was provided to us by the IDS environment, because they standardized, or de facto standardized, information models, at least for their ecosystems. All right. Just briefly sketching out the benefits and barriers. So the benefit, or the main benefit we had, is to the increased trust among participants. And we think that having this trust can help to really lower the barriers of data sharing. And following that, we can have many more use cases realized within AI and within AI pipelines, and just make it available to more organizations out there. The main barrier is probably the limited support for existing technologies. So we found it quite hard to connect the connector component with the back-end components. That was a bit cumbersome, required a lot of work. So there's definitely more work and more standardization work needed here in this regard. The conclusion, we can our main contribution is to help organizations set up their own data sovereign AI pipelines. They can draw on our insights and like inform their own studies and probably maybe follow our course of actions, which we provided a bit more detail on in the paper, and then build up their own solutions. Of course, we also face several limitations, mostly because it was qualitative data analysis, and we have kind of an organizational bias, coming from the action case study we conducted with Mondragon. So as a future work, we want to do more case studies to have more concrete design patterns and sovereign AI pipelines. So I think there's maybe a few seconds left for questions. Other than that, I would give it back to you, Lucy.
Thank you very much, Marcel. While we have the next speaker joining us, it was very interesting talk on data sharing. I think you discussed something related to standardization, but I was thinking, and also like having the sharing also the execution environment so that there's no data loss. But from machine learning or AI engineering perspective, there's a lot of discussion on feature stores. How is that instead of maybe having this standardization in the old ways of thinking in place for that? And also execution, not just for data loss, but also when doing modeling, it's quite important to have your data stores close to the execution environment for your modeling, because then there's less of data transfers and whatnot.
Yeah. These are all like other use cases that are, I think, currently discussed, because I recently heard of use case which is more of a code to data use case, because in this case it was only we forwarded the data to the algorithm and then send the more or less the result back. In the future, this will probably be different because it's not going to work for all use cases. In this use case, it worked quite well because the data sets were not so big. But in other use cases, you might want to go the different approach. So just to kind of reverse the data sharing scheme.
Yeah, thank you. We'll have more discussion when we get back. Can Hamed join?
I'm joined.
Okay, can you start sharing now?
Just a second. Can you see?
You're sharing.
Yeah, just a second. Sure. Yeah, can you see my screen?
Yeah, yeah.
So sorry for the problem. My name is Hamid. I'm from the Northern University. We work on this research with Murtaza, Professor Alhuri, and Professor Rahimi. So it's about the improving generalizability of the ML-enabled software through the domain specification. So here we use some for as you know, for the some concepts are hard to specify, so we haven't any specific knowledge, a specific definition for those. For example, considering a pedestrian, we have to partially specify what is the pedestrian for an ML software. So here we propose to use the domain knowledge. That knowledge comes through the textual or even existing data set to define for a ML module what is the pedestrian. So it's not achievable just like so every person have a different definition even. So it's very hard to specify what is the pedestrian. So we are trying to enrich this knowledge for the ML module by going through the textual knowledge and some image-based attribute to improve the understanding or perception of the ML-based module. So here our use case is pedestrian. So we are trying to show this idea by using some existing data set and image and augmenting the data set and improve the accuracy of the ML-based deep learning object detector. So here, for example, considering the pedestrian can appear in different shape, like the pedestrian on the bike or pedestrian in wheelchair. So having this agreement is very hard for the object detector. So our research question is how accurately and completely can proposed approach establish partial specification of hard to specify domain concept. And how useful are these established specification for the semantic augmentation of the data set to improving the ML-based software component generalizability? So we demonstrate that this software engineering domain analysis task can be adapted and applied to process of the engineering the machine learning software component. Also, we by use of the semantic specification of the targeted domain, here is a pedestrian, we can evaluate reason and augmented representation of the concept in the machine learning software system training data set. We propose a novel and generalizable method for deriving partial specification where the definitive specification are not feasible, and for exploiting the specification to assess and improve the semantic completeness of the machine learning software component training dataset. So as I mentioned earlier, our knowledge comes through the two sources of the textual information and the visual information. We use some online sources like the Wikipedia and the Google News to find the most highly related term to a pedestrian, and then create a semantic web around the main target, which is here pedestrian. Also, we go through the 5 data set and try to analyze it by existing object detector also, and a semantic graph generator to find the relation between the objects surrounding a concept. For example, here, as you see, there is a person and a woman walking around on the street. So we run the semantic graph generation to find out which object or terms are covered in a scene. So here there is some example of the knowledge we extracted from the text and also from the images on the data set. So on the text, we go through the Googling ground to find out what term co-occurrence with the pedestrian and what is the similarity score between these terms and the pedestrian targeted concept. Here is a pedestrian. So also we run the faster RCN and unseen graph generator, unseen graph generator to analyze the images on the data set. You see there is some terms here: bicyclist, bike, jaywalking, and motorist from the source of text, and also from the image. Then we analyze the 5 data set here: Caltech city person, Eurocity person, and crowd human, and wider person by running that faster RCN and unbiased scene graph generator. This is the detail of the detected object and the number of the distinct object. Also here you can see, and distinct relation. What is the relation between the, for example, pedestrian walking on a street, crossing a street, or so on. So here we got the city person, which is the lowest number of the. There is one of the lowest number of the object on that, and as a base data set to enrich the data set. So then here also there is a set of sample derived specification from a form of subject-object, subject predicate object tuples. As here you see, pedestrian has a bike, pedestrian has a wheelchair. Also, some safety concern we see in the textual information. Also, in the visual information, we see pedestrian is a people or pedestrian, where we can detect these such a specification on the data set. So then we wanted to find out how many of these unique how many of these specifications were uniquely in each of these data sets. For example, Caltech has just 6 unique specification which not contained in the other data set. And for the ECP and the crowd human, the number was high, so they had a most unique specification on their data set. Also, to find out how is these specification related to pedestrian, not, for example, to another concept, we run some algorithms such as the SVM decision tree to find out the classification algorithm to find out how these derived specification are related to pedestrian. We can see precision recall and F1 and F2 score on these algorithm on the derived specification. So related to the to evaluating usefulness of this proposed model, how we compare the semantic semantic augmentation based on these derived specification by how it's evaluated object detector on the base data set. Also, randomly we pick exact same number of the image from the different mentioned data set and add to the data set and train the faster RCN to find out how it's worked before and after semantic augmentation and random augmentation. So here it's our, as I said, our base data set is the city person. So we go through each data set and find augment the data set by that missing specification. So from the Caltech, we totally choose 288 from the ECP, which was the contain most missing most unique specification, about around 1,000 images, and from crowd, human, and wider. So you can see the statistic here. Then we trained 2 object detectors. One of them was the faster RCN ResNet, and also the second one is the darknet. So here you can see the result of the semantic augmentation before augmenting the data set. So we have around the 4% slightly improvement on the detection of the pedestrian on this data set. So the blue is the before augmentation performance of the object detector, and the yellow is the after augmentation. So also here you see these evaluation for the darknet, which is the yellow. We train it over 58 part and then run the algorithm on the test set. So also there was to be fair about to find out how its improvement is come through our proposed method, or just randomly adding these images can improve the accuracy of the object detector. We compared the semantic augmentation against the random augmentation. So here we have the improvement about the 2% on the semantic augmentation against the random augmentation. So adding just in randomly images improved the object detector, but if we have a method to systematically add those images, so we get a better improvement on the object detector. So our proposed method can be used for the formal benchmark or dataset collection. Also, we can see have some model verification to find how many of these specifications can covered by the by the object detector or machine learning models. Also, we can, if by setting the hazard hazard verification, we can have some safety assurance, and it has some use cases in the concept drift. So, conclusion and future work, we presented a generalizable approach for characterizing the extent to which a data set lacks a subsidiary feature of the domain concept, to exploiting the existing knowledge source to drive a set of partial specification for a potential domain concept. Also, we evaluated the accuracy and relative completeness of the established specification, and evaluated the usefulness of the derived specification. Thank you for your attention, and sorry for problem with the.
Thank you. Thank you very much. While we have other participants also joining back into the recording, can you expound on the use of this approach or its application for concept drift, because that was not very
To concept drift, it's the extension of our research work. For example, in the new research work we are working, for example, we are trying to find out by setting up a domain specification before and after of for example, considering the COVID. So before and after the COVID, to find out the domain specification, how it's covered and a concept. Here is the pedestrian. So after the COVID-19, the people wear the mask. So what's happening in the domain specification is has a consequence on the performance of, for example, a machine learning model. So we are trying to analyze it to find out how we can include the concept drift in the data set or in the model. So to evaluate the performance of the machine learning model.
Yeah. Thank you very much. Can you also stop sharing the...
Yeah, sure. Sorry.
Okay. So, I want again to thank you. Very wonderful presentation, which I could actually summarize as looking into data access or sharing, as well as data validation and how to optimize for non-functional performance or non-functional requirements around these pipelines. I wanted to ask a couple of questions that some of you have already answered, maybe related to Udava's case. Part of the pre-processing was on extracting the feature set, because much of the unsupervised learning approaches maybe were limited to Euclidean distance ways of clustering that. I wanted to ask, did you also try with DBScan, because those density-based unsupervised classification or clustering methods, they are also susceptible to noise, but also they're performing very well in large data sets. Hello? No, we cannot hear you. But also maybe a question, I think, related to Daniel while Eric is setting up was, I think someone wanted to know more about the data that was used.
Yeah, I already wrote a quick answer in the chat. So basically, we've got all the data available as part of our artifact repository that's referenced in the paper. and essentially it's model size, memory usage, latency, throughput, and hardware cost of a set of Keras and TensorFlow hub models, yeah, on the different configurations and platforms I presented.
Yeah, but also much of your work was focused on the training side of things. What if there are scenarios where training maybe with certain machine learning framework, let's say PyTorch flexibility during training, but then you might want at inference to work with maybe TensorFlow because of its efficiency aspects of it. How is your perspective of your study from this perspective that you might opt also to look at different frameworks at training time and also at inference time?
Okay, not sure if there's a misconception maybe, so just to be sure, the training we did was training of our non-functional property models, but the AI models we used and whose properties we describe are pre-trained ones. So when we did this study, our idea was that we take pre-trained, let's say ready-made AI models and look how they behave. So of course, conversion from PyTorch to TensorFlow is also something we are looking into. And I don't have results for that yet, but I hope that we're going to have them soon. But we haven't really thought that much about adding training to the whole concept yet, because we are more focused on the product using the AI model that has already been generated. And typically for training, one prefers to use the cloud and not some edge device where it would take, well, weeks or maybe even years.
Thank you very much. How about Eric? Do we have you?
Yeah, can you hear me now?
Yeah.
Perfect. Yeah. So coming back to your question about the clustering algorithms. So what we mainly have used in when testing the use cases I showed you, and also in the paper, is actually a simple k-means and also mean shift in some of the experiments. DB-scan would also be interesting. I think there lies a lot of potential in both experimenting with different clustering algorithms, but also the actual features that we extract from the subsequences. So that is something we will have for future work, to see how that will affect the outcome and the results when looking at different time series data. So, but in many cases, we have just seen that like the simple k-means algorithm, since it's so efficient, it has already produced some results that work quite well.
Maybe a question to all, and this relates to scaling, because when moving from maybe experimental setup into maybe production and operational systems, there's the aspect of scalability, maybe from data set perspective also, or maintaining the tool chains that we have in the pipeline. How is the scalability aspect taken into consideration for each of the part of the presentations that you've been doing today? So for all presenters.
I can start answering because it's quite quick in my case. We did not really take that into account, and there's a lot of work to do there. So because it needs to, in my case, we need to have more standardization and setting up these pipelines more automatically, and that will help scale them up. Because so far there's many manual work included, which we want to avoid with our work as well.
Yeah, I could answer next. So in our case, that's relatively straightforward, luckily, as once the basic toolchain has been set up, and in case of TensorFlow and TensorFlow Lite, that's typically relatively simple, even when moving to new target architectures for evaluation. The entire benchmarking and analysis process is automated. And well, if there is a lot of benchmarks to be made, then it can also be parallelized by, for instance, having 2 or 3 instances of the same hardware platform. And it's also possible to update the models later on. So when a new hardware platform becomes available, then the results for all the other hardware platforms can be reused, and just the new hardware platform or the new AI model or something else needs to be benchmarked and added to the model. So that works well, as long as all the other factors like TensorFlow version, model, training data, and so on remain constant. When they also start changing, things become more difficult.
Yes, I can go next. So I think in our case, we also didn't think too much about how this could scale. We have focused more on building a prototype with this simple API that I showed in the presentation, and kind of make the pipeline work. And then scaling up will be a challenge. So this is something we need to work more on, basically.
Then Hamed?
Can you hear me? For us, the challenging part about the data was the generating scene graph. So it was very taking time consuming. So yeah, also adding the new concept. For example, here we just consider the pedestrian to show our example use case of our method. But adding new concept like for example, car or related to pedestrian, so it's add some extra. We need to add extra sources to our work, so it's scalable. We are trying to for concept, for example, car, pedestrian, also in a different domain related to drone and so on. So it's also to solve the problem related to scene graph, we go through another models like the multimodal machine learning model to generate to solve this problem by using different model and different concept. So yeah, it's scalable, I can say that.
Yeah, and then finally, Aki, Victor.
Sure. Yes. So for my situation, it depends on the method I adopted. We adopt because some methods such as non-retraining based method need more time. For example, a new recover need more training update time due to the meta heuristics method adopted. So this time we didn't evaluate evaluate from the aspect of performance such as scalability, but this is currently we have no discussion about it, but this is one more aspect when we choose a more suitable method and coping with trade-offs between other aspects such as accuracy or consistency, or such as and so on. That's it. Thank you.
Yeah. Since there's no more question and we have 2 more minutes, we can use them by maybe each one of you stating the most critical or pain point in your work. What has it been for future work that you would like to focus on?
Yeah, so I can start again. In the case study we had, it was mainly connecting new technologies with old technologies. And this is not just the technical integration per se, but also other topics that relate to this, like having matching data models, for example, or matching vocabularies that work together. And these things, they always require a lot of manual work, and there is and that was the biggest pain point for us.
Thank you. Then we can have Daniel next.
Okay, so I think the, let's say, biggest pain point or most interesting point is not something we do already, but something we want to do. So use the data for automatically helping users configure their system, like